tornado archive, you can do a random generated event, and so this is one of the ones that appeared. And so I thought, you know what, there's actually enough data for this, so let's make a try, why not? So this is May 15th to May 16th, 1968, a severe weather outbreak that did occur, caused 72 fatalities and 1,203 injuries, which is certainly a very high total, especially compared to modern day outbreaks. And this outbreak produced many significant tornadoes across the Midwest, the Mid-South, and the northern plains, the high plains. And some of the more infamous tornadoes we'll be talking about. So one of the ones that is most commonly known with this event is the Jonesboro, Arkansas F4 tornado. And so we have some data on this tornado. And so whilst this tornado did track over a very long distance, we need to know what happened behind the event. And this is actually a profile that I managed to pick up from Chaser Archive. So shout out to any app or anything that I'll be using here. So shout out to Chaser Archive. We have a profile sounding here that is of the Jonesboro, Arkansas tornado, and we can see on the SKU-T and the holograph what really led to this sort of event. Of course, the mesoscale sort of setups that would occur. So mesoscale is sort of like the more smaller scales sort of events that can take place. We would never really know about that sort of stuff in this sort of like depiction of this SKU-T and sounding. This would never depict what else happened in the environment to cause the F4 tornado. But this is a slice of multiple slices that took part of that event to make that tornado happen. So with this SKU-T on the left, we can at least determine that we had a very significant profile. So what we're looking at here is the temperature and the dew points. You've got the temperature, the spread, and the dew point spread, and you've got the air parcel which will lift across the atmosphere, and you reach a point at which this reaches lift condensation, and then that forms a seedling to an updraft. And so we can learn from the profile what the parameter spaces that were required. And so the four main ingredients that will require this sort of setup to take place anyways before the event even took place would be the lift mechanism, the moisture, the instability, and the wind shear. And on the left we're going to be talking about the instability. And off the bat, mixed layer CAPE is going to be measuring the instability across the mid-levels of the atmosphere, and that will tell us really how favourable was it to produce these severe supercellular thunderstorms. Supercell meaning a rotating thunderstorm, and so how favourable would it be to produce a rotating updraft thunderstorm. And so when you have 1000 joules per kilogram, right here we have 1900, so when you have 1000, that's enough to cause one of these rotating supercell thunderstorms, at least a favourable organised supercell. And so we have 1900 joules per kilogram mixed layer CAPE in this mid-level, which is more than adequate. And we also have these low LCLs, these low bases. What they mean, these condensation levels, when you reach below 1000 meters, you have very low bases to the ground. So if you look up and you look about a kilometer up into the air, you're getting an idea of how sort of low the base is. And whilst in a relative comparison you are very small, that base is also very low to the ground, because normally these bases can be much higher, several thousand meters above potentially, is when you start considering high base, and what we consider this is low base. And when you look at this profile, you see high instability, low condensation, low lying bases to the ground. You have very little sin, so there's a little inhibition to the instability profile. You do have a little bit of this warm nose in the profile, which will sap sort of the low instability in the lowest 3 kilometers of the atmosphere, and that will probably be in part due to some dry air aloft when you have this temperature dew point spread right here. And this sort of nose will probably also remain due to potentially the lack of surface heating eroding that warm nose. So whilst it's there, it's very minimal, and it's only minus 17 joules per kilogram, so that's still negligible to the total sounding. and we do see some sap on the 3 Cape. So we're probably talking about more elevated instability above 700 millibars. We're talking to contribute to the profile more so, and some colder temperatures aloft. So you see around just above 700 millibars is the freezing level, and there's some instability just below that, and there's some instability above. There's actually quite a lot of instability right above the freezing level, which would probably suggest this supercell probably produced very large hail as well. And you can see that the temperatures do cool off -20 degrees within just below 300 millibars, so quite a cold profile aloft as well. And so when we look at the hodograph as well, because you have to overlap the instability profile with the hodograph to understand more of the picture of what was the supercell like, not just in a thermodynamic environment, but how did the wind shear sculpt and produce this rotating mesocyclone that produced the tornado. And wind shear is probably the highest percentage of influence of any parameter space that would direct a significant tornado to be produced from a mesocyclone. And so you have to take a lot of weight on the consideration of the event with the hodograph. And so in this hodograph, we were measuring the way the winds rotate, how they veer, so they change direction and they change in strength into the atmosphere. And one of the things off the bat that you immediately see in this, which isn't necessarily all that favourable, is you get southwesterly winds. You would want to see more backed southeasterly winds to allow for this sort of rotating storm to produce a tornado. But we do have these veered winds that are from southwesterly near the surface, and whilst that still is the case, the winds do strengthen quite a bit to 50 knots above 850 millibars, and we do see fairly enough minimal storm helicity values of 140 meters squared per second squared, and just enough bulk shear in the lowest kilometer. And I think a better way to demonstrate the actual part of the hodograph that would represent the large amount of this area that's covered of the hodograph in the lowest 3 kilometers is through this parameter right here. And so we've got 260 meters squared per second squared of SRH, which is more than adequate. That's about 1.75 times more than what you would need typically for a rotating storm, with enough bulk shear of 37 knots. And once and you have the streamwise vorticity. Once the streamwise vorticity normally is favourable at 0.025, you have it in the zero. You have that just about that favourable level right in the 0 to 1 kilometer level. So that is a very favourable profile right there. And you have somewhat large, around, not too large actually, you'd have about 20 knots of storm relative inflow. So actually I'm probably seeing a classic supercell in terms of its size. And what you can do is you can also translocate and produce an image of the supercell using the hodograph. So if this was your base of the storm, you would draw the base here, and then you draw the supercell around the hodograph. And so if you create a shape of almost like an N shape, that's your supercell. That's what the supercell most likely would have looked like. And of course, I don't have a radar axis, but there's a pretty high probability that that is what the actual supercell looked like if you translocate a hodograph profile to the actual supercell characteristic. Another shout out is the Tornado Talk website, and this is a really beautifully crafted website that a lot of people should use and check out and read from. This gives a quick summary, and this does show the F5 Charles City tornado, and you can see it is in this frame. They probably captured it likely near peak intensity. You can see the almost large wedge shape. It's kind of a hybrid stovepipe wedge shape, but you can clearly see the dust cloud at the ground, the full deep condensation, and you can see the way it's slightly elevated base actually. So the base is slightly elevated, but you still have a lot of mass, a lot of condensation that's reached the ground, and you probably would in theory have to require a large pressure deficit to produce the condensation of this extent from a higher base. The higher this base is, the more that pressure deficit you sort of need, and also the larger the sort of condensation is, where you can see this sort of like this high condensation gradient, and this would kind of imply that this tornado is near peak intensity. And once the damage, this picture doesn't show anything about damage, you could probably suggest that this probably was at least of high-end F3, F4 intensity. Of course, I think a better way to measure the intensity is using the EF scale, because the EF scale demonstrates intensities based because its intensity is separate to the damage, but you can use the intensity scale to sort of represent the range in which the tornado intensity will lie, because some of those older F scale intensities were overestimated, so it wouldn't really represent what you're trying to describe visually as you're looking at the tornado. So high-end EF3 strength, high-end EF4 strength is almost a certain when you see an image of a violent tornado. And this is a picture of, again, shout out to Tornado Talk, this is a picture of the Ole Wayne. I believe it sounds Dutch to me, but this is the F5, the other F5 that occurred. And one of the things that I noticed is that it's actually a surprise. Back in the day, there was more leniency to the rating of F5, and so this tornado was rated F5. But the damage, if you were to sort of do a modern day EF scale assessment of it, most of this damage would actually likely be in the EF3 to EF4 range. Yes, you have some of these down the houses, but these sort of damage indicators nowadays would only represent maybe the high-end EF3, low-end EF4 rating, and maybe even mid-range EF4 rating, depending on the descriptions, because not all images are shown here of all the damage, but the highest I could assume in the modern day scale would probably be mid-range EF4 from these sort of pictures that are shown here. So that's just a fascinating thing that is because one of the most interesting things is when you're looking at old tornadoes, you want to be able to relate them to the current day and age and the sort of standards that are put in place now. And with seeing what happened then and trying to give a visual perspective of what it would be like now, or what we think of it now, is a very intriguing sort of idea. And if we put that to shape, again, this tornado's damage is probably of the EF3 high end to EF4 damage from these images, and it could be slightly higher based on the descriptors from the damage that was not shown in these images. Last but not least, we can tell that this is a high OIS, so I would like to give a shout out to Thomas Grzulis, which is a tornado expert and a legend that I think most people know of. This will be considered a high OIS intensity scale outbreak, and you can even use the other intensity scale to measure the significance of the outbreak, because if you just look at this alone, you've got 46 tornadoes, and of that a high proportion of strong tornadoes, and you have 7 F3s, 2 F4s and 2 F5s. And so if you compare that to a modern scale sort of outbreak, that will be very high up the scale in the OIS damage, and also just the significance of the type of tornadoes that were produced in the outbreak. Alright, on to the second part of the video, and this is redone, this part of the video, because the first part of the information was outdated, so we're continuing with this part. But now we're looking onto the NHC most recent outlook. So this is looking at the 10 to 70% disturbance. This is right after Eric, and now we have this new disturbance that will take the F letter of the Eastern Pacific, and there will be some further development that's also possible after this, but for what we know in a medium to short range, this will develop. So this is something to watch out first, and I think we should use the GFS first before we use the GEFS, the ensemble guidance. And what this is going to show us is the development of this system. So it's currently like originating roughly west of Nicaragua and just south of Guatemala. And if we just play through the loop, it should appear, so it appears within just hour 54. We now have certain guidance. When I was looking at this last time, it's hour 72. Now we've got even closer range, obviously, because we're getting closer to the time for it to development. But there is still that continued development expected within this part of the region first, before the system moves across. One of the things that's actually changed now with this system is the track. The track has changed from what was initially more along the coast and riding across the coast and then fizzling out, just like several of the other systems that have followed this similar track. Now we have less so of such, and now we have this sort of much closer to the coast and dying out due to land interaction. You have the mountain range here, which should prevent any further development, and also very close to landmass probably results in interaction of the eastern quadrant of the system if this was to take place as a scenario. So that is something to watch out. The previous model runs, actually, if we just go back to 6Z 0Z has very little development, and 18Z. Okay, we've got a lot of different scenarios panning out, and the further out you go back before the most recent runs, it gets more uncertain. But if we just look at it now at this point, the system is right here, and we go back to 6Z. It's still much further back, but it's still along the coast, and 0Z is not even developed, and then 18Z it's along the Mexican coast, and they are further out. There's more uncertainty. So one thing that has arrived in more recent model runs is the confidence of the system along the coast and potentially riding at just parallel to the coast, which has the potential for any deviations to cause a dramatic difference between whether it moves offshore, intensifies, or if it weakens along the coast, or if it maintains and strengthens along the coast and dissipates at higher latitudes. So there is more certainty with development and potential intensification, because the previous runs, especially the last 0Z, did not show much development, and there's quite a low probability scenario now, given that the NHC is confident with the development of this system, and the fact that the more recent model guidances are in alignment with each other and showing development along the coast rather than the more outdated runs. But now if we look over to the GEFS ensemble guidance, we can make out the same system with development, and it does not actually develop. This is an ensemble guidance, so not necessarily the most robust runs will be demonstrated, and not necessarily the least robust ones will be shown. It's just like an average of them all. So the main thing here is there is precip here, and there could be some development this way. GAFS is also a bit wobbly, only moving more westward, which is actually more in line with what the NHC kind of has, as it doesn't necessarily show an early recurve. The kernel of uncertainty does project it that way, but that's the far eastern side of the probability zone, and if the current track of this does not necessarily reflect the current GFS runs. But again, this is an early probability zone before the developments even occurred, so the GFS might be more on point, especially because this is now in the GFS run sort of range within that hour 54 to hour 200, as opposed to the ensemble, which is typically more than 200 hours out. In fact, sometimes several days out. So there could be a bit of moral uncertainty with the ensembles now. But there's certainly some development here, and then not necessarily to be taken much with any seriousness. There is potential room for more development out here. The development is much less robust now, shown after the current system with probability, but there is potential for more. development in this region. One of the things you can also see is you can see the wind plots. So you just look at these sort of wind plots and you can see this is going to be the North Pacific High, which we have to just pay attention to, because if we look at the runs, the North Pacific High noses in and maintains its strength with this anticyclonic flow around it, and then you've got this offshore flow of very weak westerly flow, which is going to be maintaining this sort of surface, like this sort of track along the coast for this development. And so any other tropical wave that is propagating across from the Atlantic side just to the south near Panama would propagate across and likely be pushed into the same track. And this is just a GFS, but the North Pacific High is still it remains there, and the track and the similar surface pattern to what's shown in much closer range for the current system. And for this we can still use the GFS, and in its much longer range it also shows that North Pacific High there. And if we look at GFS plots on the shear remains largely low for the longer range in the guidance, which is similar to what's currently presented for this current development system. This system is expected here under a low shear environment with the vorticity propagating along the near surface 850 millibar flow pattern, with this sort of weak offshore flow and a nosing North Pacific High, which is, I guess, what is kind of similar to late last year, and also around when John happened, you had this North Pacific High diving in, and also it may be in part due to the larger scale neutral Enzo pattern and the current DPO phase around that is horseshoeing, allowing for the North Pacific High to nose in like this. And the Enzo neutral pattern probably has a larger impact on it, and the same pattern is in the long range as well. This is the climatology map, and the climatology map does show this sort of NPO, should I say, and DPO oscillation, these cooler waters that could probably support the idea of the North Pacific High being shunted down probably a little bit more further south, which allows it to nose in much more. And also the North Pacific High is dominant. This pattern, or any pattern, is not disrupting the high. There are not any sort of equatorial lows or from like large Rossby waves that propagate across that weaken and suppress the ridge, and there are not really any ways for the surface pattern to provide for strong westerly flow around the system, or even just more equatorially pushed south waves that propagate across from Panama. So there's a lot of development that goes across and just along the Mexican coast currently, where in the longer range it'll probably change, where we do see these longer tracks across the Eastern Pacific. That's looking a bit messy now, but looking at more tracks that go westward, whereas currently we're looking at tracks that go near the Mexican coast. And this is a favoured pattern this year that will maintain on the large scale, and in part due to the Enzo neutral phase with this DPO phase, and also in part due to, well, it could also be in part due to any costero sort of events. So any sort of El Nino costero could enhance activity in the Eastern Pacific. Also a warm West Pacific sort of oscillation should allow for this sort of flow and ridging system, these larger synoptic systems, to maintain as they currently are. These two closed patterns right next to the Eastern Pacific Basin should be a larger scale influence on the way the synoptics play with the ridge trough pattern, and also the sea surface temperature patterns for what we're seeing here. Particularly you have cooler temperatures here, and that prevents any development north of this latitude, and prevents much development west as well. So you have a very short-lived life cycle of development. And the 7-day change from recently, you can see the upwelling that has taken place where Eric has been around this region right here, and this is going to be where the current cool neutral is currently occurring, and there's still some upwelling and some warm sea surface temperature anomalies in the region as well. One thing, however, that is not shown in this map is that any anomalous pattern to favour development out west would be in part due to high oceanic heat content values in the Eastern Pacific, open Pacific sort of region that are anomalous this year and above average compared to previous years. So that would develop any more intensifying storms that do travel further west. Also, one thing is any Kelvin wave propagation should shut down the Eastern Pacific development once that does occur, and any sort of MGO propagation that does occur in the Central Pacific should increase the activity in that period of time. And so that might be slightly different to the climatology that would be expected at that time, similar to 2018, where you did have that sort of pattern and you had these very persistent systems that moved across, and also a lot of ITCZ development that allowed for tropical systems to develop that equally moved onshore and largely also moved out west, particularly out west, and that sort of pattern was anomalous, and particularly due to the larger oscillatory pattern and the anomalous MJO pattern, which is more of just a low probability event of happening rather than a predictability. So there's much less of a percentage confidence that I was just fully driven by the oscillation pattern of where the MJO propagated over, and there is some low probability sort of chances of an intensifying MJO phase, and also the frequency of this sort of MJO phase, and when the sea surface temperature is also favourable at that same time when the MJO appears to favour that. So that would have a larger scale influence on why 2018 was particularly favourable, and we don't see that as much. We only see small scale differences, so any system that does travel up west will be small scale influences. And with that, if there's any sort of things that I missed out, or you guys have some questions, then do comment below. I'm curious to know what you guys' thoughts are, and I have actually shared some of these thoughts on Storm Chaser coaching, so if you ever are interested, we discussed stuff over there as well. So without further ado, I'll see you guys on another video.